Good afternoon, everyone. This is our first matrices video lecture for our online instruction here. So this is the kind of second set of material that I will post for this week. So far you've had material from 6.1. I had a couple videos there totaling just over an hour's worth of material. Think of that as like Monday and Wednesday's material. Wednesday, Friday material will be this lecture here, and I will post another example video just after this one. But basically the rest of the semester we kind of have this week, and next week is really it, and then a final exam. I'm not exactly sure the details of that final exam yet, but I will get you those as soon as I know them, as soon as I find the best way to figure out how to administer that final. It might be multiple quizzes. It might be kind of exams broken up over the course of the week. Not this week or next week, but in the future. But I will be as transparent about that as I can, and once I kind of make a decision and figure out what other instructors are doing. We're all still kind of waiting for guidance with assessment. But that being said, this material you have this week. Next material next week I'll post videos back in chapter 4. I know we've talked about some of that already, dealing with subspace and basis. We'll revisit that just a little bit, and I'll post another lecture or two about 4.2 and 4.3. That's really all the material that we cover in this course. So we're just about done here. But we do have a quiz this week, this Friday. That I will post Friday morning, and you'll have pretty much all day to take that quiz. It will be, of course, on WebAssign. It's the best way that I can get that to you. WebAssign type questions, right? Similar to the homework. You'll have a couple submission attempts. So you'll take the quiz, submit it. Say you get a 6 out of 10, for example. You can take it again, submit the whole quiz again. Say you get now a 9 out of 10. That'll be your quiz score for quiz 2. Each of those quiz attempts will be timed, so you'll have, say, 20, 30 minutes, I'm not sure exactly, once you open the quiz to take the quiz and submit it. But that's also why I'm giving you multiple attempts, at least for this quiz, to get things kind of figured out and make sure that you understand the parameters of the quiz and that kind of thing. If you have any questions about that at any point, just let me know. Send me an email, message on Canvas, or post to the discussion board that we have up there. Other than that, I'll still hold office hours at regular times for the next 2 weeks. But yeah, so here we go with our first video lecture. This is 6.4, which I thought previously was 6.6. I apologize. 6.4 indeed is what we call systems of differential equations. Okay, so the idea behind this is that if we have a differential equation, not only one, but a system of them. Now, we're probably not going to deal with anything larger than, say, like a 2x2 system, just for simplicity's sake. But of course, as many things in this course, this extrapolates to higher dimensions. And I'll kind of talk briefly about what a differential equation is for those of you who haven't had that sort of material yet. And then I'll talk about kind of what's pertinent to us and how we find these. It has a lot to do with eigenvalues and eigenvectors. So that process is embedded in solving these differential equations, and it's rather pretty straightforward. So here we go. Basically what I'll be doing is talking over what I've recorded here, or the notes that I've taken. So I'll be slowing things down and speeding them up and bouncing around just a little bit. I'll try to be as clear as I possibly can. So just bear with me, and of course you can pause and rewind and do all that at your leisure. Okay, so what exactly is a differential equation? I already got to slow this down. What is a differential equation? Well, pretty much just any equation that involves derivatives. That's it. I mean, it's just a differential equation. For example, dy dx equals lambda y, where we say lambda is a scalar and y is a sum function of x. So what we're really asking here is which function has a derivative that is just a scalar, lambda, times itself. All right, that's what it means to say dy dx equals lambda y, or y prime is lambda y. The derivative is equal to a scalar, lambda times y. And what I want you to notice is that's very similar to our eigenvalue, eigenvector problem, right? A v equals lambda v. When I apply a vector and a matrix, when I multiply, what vector gives me just a scale of that vector back? This is a very similar type question, and that's why those eigenvalue, eigenvectors are going to be an important part of this here. Okay, so first thing we want to do, let's just solve a basic differential equation where we have dy dx. I'll very quickly change x to t in the next couple examples, but for now we'll just use x. So the derivative of y with respect to x is a times y. So it's a scalar a times the original function. Right? We can think about maybe some types of equations where that would happen. If I take a derivative, where do I get the same function back? And we're pretty much stuck with exponentials, right? Derivative of e to the x is e to the x. It's the same equation back. There's just got to be an extra scalar a involved. Now, there's a rigorous way to show this, and I'll do that here. Basically, what we do is we separate. So what I've got going on here is I've kind of multiplied both sides of this equation by dx, and I'm also going to divide both sides of the equation by y to get dy over y is a dx. Okay? The reason I do this is it allows me then to integrate both sides of this equation. But what we have here, this is what we refer to as a separable differential equation. This implies the differential equation dE is separable, right? I can separate y's from x's. Okay? And now I integrate both sides, okay? To undo what I've done to y here, right? I've got like dy over y. I want just y. I want to find y so that it satisfies that differential equation that we started with. So I undo the differential by integrating, okay? Excuse me. So when I integrate dy over y, that antiderivative should give me a natural log of y, and the right-hand side should give me antiderivative of a dx should be ax and then plus a constant. Right. I'm just going to change colors here. Instead of A, I'm going to use that kind of orange-brown that I used before. So ax plus c. Now, technically, we might need c on both sides of the equation there, but I really only need one constant of integration. I don't care about more than one, just one. And now I want to solve this equation for y. I want y equals. I have a natural log. I undo that by exponentiating. Right? I exponentiate. Okay, so when I do that, I'm left with y equals e to the ax plus c. Now, what we typically do here is break things apart. That plus c in the exponent, I can treat as like a product of the bases, right? So that's e to the c times e to the ax. But e to the c, e to a constant, is a constant. So what we're allowed to do basically is rewrite that e to the c as just kind of c. Right? E to the c is a constant. I replace it with c. I don't care exactly what that constant is. In this case, I'm just finding what we call a general solution to this differential equation. So basically what we'll end up with is c e to the ax. This is the solution. Okay? Not all differential equations are this kind of straightforward. Not all of them are separable. Okay? We won't be dealing with a specific singular differential equation like this. We'll have a system of them. Okay? So now what I want to look at, I want to try to generalize this maybe just a little bit more. So when we go for, first, I misspoke, got ahead of myself. I want to verify that that is indeed the solution. And all it really takes is a quick derivative. If I take the derivative dy dx of that c e to the ax, I should get a times y back. All right, so the derivative of c e to the ax with respect to x is going to be c e to the ax times an extra a. Right? But that's just, of course, a times y. That's it. It's just a times y. There's nothing else to it. The original equation is there, c e to the ax, and there's an a out front. It satisfies my differential equation. Okay? Now, another thing we'll want to be able to handle is what we call conditions, right? Very frequently are we dealing with a differential equation that has some specific stipulations set to it, right? For example, in this case, say we have some initial condition, the same differential equation, subject to y of 0 is minus 1. Okay, this is called an initial condition, right? And it's initial because I'm thinking about x being 0, right? When x is 0, y is minus 1, kind of at time 0, initial time. I'm just dealing with x's in this case. So it's just initial x gives me a y of minus 1. And really all that entails is plugging in 0 for x, setting that equal to the y value, the corresponding y value, minus 1, and figuring out what c is. Basically, an initial condition will provide to you a way to figure out what that constant of integration is. So, when x equals 0, y equals minus 1, I plug in 0 for x, so that's c e to the a times 0, that's c times e to the 0, which is just c, right? C times e to the 0, c times 1, and that is all y0. Well, y of 0 is minus 1. So my solution is then minus e to the ax because c was minus 1. So I take that original solution, c e to the ax, and I know what c is because of my initial condition. Okay, we'll do some examples like this. So that's just a basic separable differential equation there with an initial condition and kind of without. Without, there'll still be c's left over. With, we'll be able to determine what those c's are. Okay. So now we look at a system of linear first order differential equations. There's this whole classification for differential equations, and for us, all we really care about it is linear algebra, right? And that it's a system of differential equations. So what we'll be working with is something that looks like this. Say y1 prime equals ay1 plus by2. y2 prime is cy1 plus dy2. Okay, and I'm using that a, b, c, d on purpose. Of course, we've seen things like this before. I typically put that sort of thing in a matrix. I think you're getting the idea. But this is a system. I have basically two differential equations, and they're kind of related to one another, right? Each one has a y1 and a y2 involved. I don't necessarily have to have all of those. This is just kind of the most general case that we work with. I could, of course, have a y3 prime equals some sort of other coefficients, and y1 and y3. There's of course, a bunch of possibilities. We typically look for square systems here, right, of course. But what we tend to do here is we tend to organize this a specific way. I pretty much want to write this as a matrix vector equation. So what we do is we let y prime, just y first. Let y here in blue equal to, let me slow things down. That's just y1 and y2. But that means that y1, or y prime, the vector, is y1 prime, y2 prime. So we're taking, y in a vector form to be y1 and y2. Those are basically my solution vector. Then y prime is the derivative of those solutions. And then in green here, I'm going to say A, the matrix, it's just going to be those coefficients, A, B, C, D. Right, it's that easy. Now, if I want to kind of extract this equation, what we have is y prime, the vector, is equal to A times my, skipped ahead a bit. But there you see it, y1, y2 vector times A. All right, so at the bottom there you see the derivative vector, right, y prime, is equal to A times y. That's a general form of a system of differential equations. Y prime is equal to AY. So basically what we're trying to figure out is what sort of y's that when I apply a to them, is it the same as taking a derivative? Okay. It works very similar to a constant kind of being brought out. It's very similar to kind of that exponential that we talked about before. Okay. Oh, I'm sorry. So what we do here, from before, when we solved that differential equation, we found that we had some solution that looks like an exponential. Now, from that, we expect that a solution to a system, y prime equals ay, should look like something like this. Y equals u1 e to the lambda 1 t, u2 e to the lambda 2 t. Now, of course, those lambdas are very likely those eigenvalues, and the u's then are probably the corresponding eigenvalues. So I'm not showing you in too much detail where this exactly comes from, but I don't think it's such a far jump coming from solving y prime equals ay to get to this new sort of matrix equation where now I have vectors and a matrix instead of just functions and a constant, that my solution should still incorporate kind of then a vector of exponentials. Right? So what I write here is that this is e times lambda t times the vector u. Okay? So what we need then, we'll find through this sort of computation, if I take, let's see what I have here. If I take y prime equals lambda y, right? That's our general form of our differential equation. That should be the same as y prime equals a times y. So what I'm kind of seeing there is lambda y equals ay, and we'll get there. But what I assume the solution looks like then is e times lambda t times the vector u. Now, times lambda, what I see then, when I move some things around, that's the same as the exponential y prime equals e times that exponential times this vector lambda u. Okay, and I also know that y prime is equal to, and ay is equal to a, and again, y is assumed to be that e to the lambda t times u. I know that's also equal to y prime, right? Y prime equals a y. Right? But if I manipulate things again a little bit here, that's equal to e to the lambda t exponential, and then a times u. These guys have to be exactly the same, right? Because both of those equations should be equal to y prime. And if that's the case, if au should be lambda u, let me write that. This implies that au should be equal to lambda u. That's exactly our eigenvalue-eigenvector problem, right? This means that y equals e to the lambda t times u when lambda is an eigenvalue and u is the corresponding eigenvector. Sweet. So what that means is if we have a system of differential equations, as long as we can pull away from it this matrix A, all we need to extract are the eigenvalues and eigenvectors of that matrix. And once we have those, we have solved the system. Okay. But how does that equation look, right? We see this e to the lambda t times u. Let's expand on that a little bit. So this equation here, this differential equation, has a solution e to the lambda t u when lambda and u satisfy AU equals lambda U, right? That's our eigenvalue eigenvector problem. So I'm just summarizing what I was talking about there on the previous slide, that this eigenvalue eigenvector problem is kind of a direct consequence or how I solve the differential equation. So in other words, what that means is if U1 and U2 are distinct eigenvectors, and there's associated lambdas that are also distinct with distinct eigenvectors, eigenvalues, forgive me. See, I spelled it wrong there. Let me change that. This should be eigenvalues. Okay. Then the solution will look like y equals C1 e to the lambda 1t u1 plus C2 e to the lambda 2t u2. Okay. This we have to know, right? This is the form of a general solution to a 2x2 system, right? This does extrapolate to a 3x3 system. I will just add another term, right? There should be 3 eigenvalues from a 3x3 matrix. There doesn't necessarily have to be, but there should be 3, and thus we can find the solution to a 3x3 system of differential equations, right? But this is the general solution for the 2x2, and I'll use this to then solve the next problem here. So it's a little bit involved, right? But in practice, it is really pretty straightforward. So I want to get to you an example here. Let's solve y prime equals minus 3y1 plus 2y2, and then y2 prime is 3y1 minus 2y2. So there's my system of differential equations, and what I want to do is write this in its matrix vector form. So I say that what I have here is the derivative vector, right? y1 prime, y2 prime is equal to my matrix A, minus 3, 2, 3, minus 2, times my solution vector, y1, y2. Okay? This system has a solution if I can find eigenvalues and eigenvectors. Okay? So I take my matrix A, and I'm going to find eigenvalues and eigenvectors. We need eigenvalues and eigenvectors of A. So what I need is the determinant of my A minus lambda I, right? So there that is. It's the determinant of minus 3 minus lambda 2, 3, and then minus 2 minus lambda, right? Of course, in the last video I posted, they did things a little bit differently, right? They did lambda I minus A. It does not matter. Just kind of pick a way that you like and stick with it. I always have done this way, A minus lambda I. So I find that determinant. This is a 2x2 determinant, so I can just find the product along the diagonal. So that would be minus 3 minus lambda times minus 2 minus lambda, and then subtract the product of the off diagonal. That's 6. So when I then distribute all this, I get a minus 3 times minus 2 is a 6, and then the sum of the next two terms would be 5 lambda plus lambda squared minus 6. Okay, so again, working with that characteristic polynomial, simplify it down as much as you can. I'm finding the eigenvalues, right? So the 6 and minus 6 cancel, and I'm left with lambda squared plus 5 lambda. And that I set equal to 0. My characteristic equation then is lambda squared plus 5 lambda equals 0, which I factor to lambda times lambda plus 5. And again, I set that equal to 0. My eigenvalues are then 0 and minus 5. Okay, so I'll show you where those go in my solution to this system here in just a second. Those are my eigenvalues, 0 and minus 5. In my solution, so y should be equal to C1 e to the first eigenvalue times t, so that's 0 times t times the corresponding eigenvector, plus C2 e to the second eigenvalue minus 5, t times the corresponding eigenvector u2. Okay, so all that's left then is for me to find u1 and u2. I need those corresponding eigenvectors. So I have two eigenvalues. One is 0. That's kind of interesting. I just need then the corresponding eigenvalues. Or I'm sorry, eigenvectors. So we now need the eigenvectors. So first I look at lambda equals 0. Lambda 1 is 0. I need to find the solutions to a minus 0I times u equals 0. Right? That's the equation that we solve to find eigenvectors. Right? So I take a and I subtract 0 along the diagonal. Well, then that's exactly a. Right? Minus 3, 2, 3, minus 2, augmented with the 0 vector, and I reduce. I reduce to solve the system. So I go through the reduction here. I can eliminate the second row because it's a multiple of the first row, minus 3, 2, 0, 0, augmented with 0, 0. Okay, which gives me minus 3x1 plus 2s1 equals 0, right? There's a free variable because there's no pivot in column 2 of that matrix. Solve for x1. x1 is equal to 2/3 s1. Okay, there is my first, gives me my first eigenvector. So then u1, the corresponding eigenvector, should be 2/3 and 1, a vector. Okay, I could make that a little different, right? I could write it as, say, something like 2, 3, right? If I were to factor out a third or multiply top and bottom by 3, I'll stick with the first one for the remainder of the example, that 2/3, 1. It doesn't really offer too much difference. It's just a scalar. But there is my eigenvector. So that's going to show up right where u1 is in that general solution. I now need u2. So I work with lambda 2 is minus 5. Okay? And I solve the same problem. A plus 5I times u equals 0. Right? And I did plus here because it's minus a minus 5. Right? So I'm going to add 5. I'm subtracting a negative 5. I'm adding 5 to the diagonal. So that'll be the matrix 2, 2, 3, 3, augmented with the 0 vector. Okay? And I reduce again. Right? So again, the second row is a multiple of the first. I can convert the first row to 1, 1, 0. The second row I can then eliminate and make 0, 0, 0. Okay, so just reducing here, going through it rather quick. What I get then is that x1 plus s1 is 0. So x1 is minus s1, meaning my eigenvector u2 is negative 1, 1. Right? So again, I'm taking the solution to those, to that a minus lambda I times u is 0. I'm solving that matrix vector equation by augmenting with the 0 vector to find those eigenvectors. Okay? Now, from here, how does that show up in my solution? So what I've got are my eigenvalues and eigenvectors there, and they're corresponding. And I just write the solution. So, going back to what I saw before, the solution to this system is C1 e to the lambda 1t u1 plus C2 e to the lambda 2t u2. Okay, so I'm really just going to plug and play here, right? I know what lambda 1 and lambda 2 and u1 and u2 are, so let's plug them in. I've got them in different colors there. So 0t minus 5t u1 and u2 simplifies, of course, right? I have e to the 0t, which I can write as just 1 times u1 plus c2 e to the minus 5t. There's my first eigenvector, second eigenvector. Okay? So, that's what my solution looks like. very frequently we write it in its component form. So y, remember the vector y, has components y1 and y2. So I will very often write things like that. And basically what we're doing is computing this kind of vector product addition that we have going on here. I multiply C1 by both the first and second components of U1, and C2 e to the minus 5t times the first and second components of U2, that minus 1, 1. What I get from that is as follows. Y1, Y2 is equal to 2/3 C1 plus a negative 1 times C2. That's why you see a minus C2 there, e to the minus 5t. Then the second entry, that's all y1. That's all y1. Think about that as being the first components of both of my eigenvectors there, multiplied by their coefficients. Now, when I go down to the second entry in those eigenvectors, that 1, 1 down below, I see C1 times 1 is 1C1 plus C2 e to the minus 5t. There's my general solution, right? Y1 is that first coordinate, Y2 is the second. That's just in vector form. Okay? So that is how we solve a system of differential equations. It's all based on the eigenvalue eigenvector problem. So now, say for example, I had some initial conditions. If y1 of 0 is 5 and y2 of 0 is 15. Could be anything, but I had some initial conditions to go along with my system here. The first equation at time 0 is 5, and the second equation at time 0 is 15. How do I handle those? Well, I know what y1 and y2 are, respectively, and I'm going to plug 0 in. So there's y1 of 0. All right, I literally plug 0 in. There's only one t right in y1. 2/3 C1 minus C2 e to the minus 5 times 0. Well, e to the 0 is just 1. That's 2/3 C1 minus C2. That should all be equal to 5. And I do the same thing for y2. C1 plus C2 e to the minus 5 times 0 is C1 plus C2, and that should be 15. Okay, what I've got there are two equations with two unknowns. Equation 1, equation 2. Two unknowns, C1 and C2. I just need to solve for those. That's basically the first half of the semester. That's a 2x2 system, two equations, two unknowns. So I set up a matrix. 2/3, 1, 1, augmented with 5 and 15, and I solve. So I reduce, multiply that first row by 3, leaves it a little bit easier to work with. And I can then eliminate the second row, or part of it. I can eliminate below the 2 by multiplying the second row by 2, 2, and then 30, and then subtracting 2 times the first row from the second row. That's what I end up with there, that 2 minus 3, 15, 0, 5, and 15. Okay. I can work with this. This tells me that 5C2 is equal to 15. That, of course, means that C2 is 3. From that, I can use 3 to find what C1 is, right? 2C1 minus 3C2, well, C2 is 3. 3 times 3 is going to give me a 9, so this will say 2C1 minus 9 equals 15. That's the same as saying 2C1 equals 24, so C1 is 12. Okay, so I have that C1 and C2. Very similar to how I found them before. It's just now the way my solution is I've got two equations and then two unknowns, C1 and C2. And those are prevalent in both solutions, Y1 and Y2. Okay. From here, I just plug them back in. C1 is 12, C2 is 3. So Y should be 12 times my first eigenvector plus 3 e to the minus 5t times my second eigenvector. So where C1 and C2 were, I've plugged in 12 and 3 respectively. And now to write this in its component form, right, Y1 and Y2 separately, I have 12 times 2/3. 12 times 2/3 should give me an 8. 8 plus negative 3 e to the minus 5t, right? So that's 3e to the minus 5t times a negative 1, and that's why you see the negative 3 out there. The second component will be 12 times 1, so 12 plus then 3e to the minus 5t times 1. That's y1 and y2. And I have a solution to a system of differential equations with initial conditions. Okay? So I want to do another example here. It's going to be uploaded in another video. I'm just trying to do it separately, break things apart a little bit. I believe there are some in the homework where you work with 3x3s. Okay? So in the next video, I will kind of illustrate how that happens, but basically just another example. If you have questions, please don't hesitate to write me a message, whether it's email, Canvas, the discussion boards, on WebAssign as you're working through the homework. That homework isn't due until, I believe, Sunday evening. So you still have plenty of time to explore how to find solutions to systems of differential equations. But the homework is relatively short. I think it's probably around 10 questions. I don't remember exactly. Okay, I hope you enjoyed. Let me know if there's anything else I can do for you. Other than that, have a nice day. Take care.